now so far is we've defined aromaticity, and we're interested in this because it's a way of identifying these highly stable compounds which will affect their reactivity. Okay, and this definition of aromaticity is this idea of cyclic, planar, conjugated, and each 4 and plus 2. Rather than having this be a laundry list of different check marks to make, hopefully by using these structures and these orbital diagrams, it provides some sort of a structural perspective as to why this is, as to why we can get this extra stability when we meet these criteria in these aromatic compounds. All right, so I know this is a lot of information, but hopefully, again, seeing this systematic approach makes it fun to go through and figure out the aromatic or not. Okay, so now let's pause here for 10 seconds as we're going to shift our focus a bit. Any other comments or questions about this aromaticity? And I'll put some of these in our practice problems. Oh, and actually, while we're at it, Kara, there's a quick 10 seconds, is this made me think of it, is that you don't necessarily just have to have one ring. That was where the original definition came from. But however, we said here, this indole is aromatic or quinoline. So you can go through, if you would, for fun, and then see if these meet the definitions of aromatics. Just assume they're all planar. You can see they're cyclic. And then you can go through and think about what's going on with this nitrogen and purine, which electrons could contribute to aromaticity, and so on. And what if you do have two rings, such as the purine, indole, and quinoline? Okay, so now in our last bit here today, we first find our notes. There we are. And I know we're kind of jumping back and forth. But now that we've discussed this idea of aromaticity and put that in some structural perspective, let's go back to our idea of reactivity here. And I was hoping then today that we can at least go through one reaction mechanism of one of these key reactions, because then over the weekend, we can then see that these are actually all variations of the same theme. So to start thinking about the reaction, remember from a little bit ago here, we said, I'll just put it here so we have it at the same place. We can take this lopsided benzene. Again. So of us, how many benzenes are we at now? We'll include this one. Must be about 25. We can react this with or treat this with bromine, or mix it together with bromine. And no matter how long you wait, you'll really see there's going to be no reaction. However, we then said, if we take benzene and treat it with bromine in the presence of a compound we haven't seen before, iron tribromide, FeBr3. Oh, you stopped counting. Okay. We'd end up actually having this substitution reaction. So we replaced a hydrogen with a bromine. And it could be any hydrogen. They're all the same. I'm just putting in the upper right for convenience, plus HBr. So this was our example of we're going to use a strong electrophile. So electrophilic, it's on an aromatic system. Aromatic, and we're substitution, a hydrogen for a bromine in this particular case. And what we will see is that we're going to have our 5 key reactions where our electrophile, what's going to be substituted here, or substituted in, is going to be different. From a bromine to a nitro to an alkyl group and so on. However, the mechanism that can be used to explain this reaction is highly similar amongst all of these different 5 reactions. So we'll list all of those things at the end. I wanted us to at least go through the mechanism and think a little bit about the energetics. And basically, we need to have, there's 3 steps. So 3 mechanistic steps. And let's see if this can explain this observation. the first thing we're going to do is we're going to generate a strong electrophile. And this is what will be different between our different mechanisms. We're going to have different, I'm writing what I'm saying, trying to write and talk at the same time. So strong electrophile. So we're going to see a couple of different ways to generate our strong electrophile. Our electrophile in this reaction is going to be the bromine. And so let's think about what might happen. So back in OChem 1, that bromine can add across the double bond. So you could have a nucleophile attack the bromine and kick out bromide, for example. So we do have a potential intermediate dipoles here. One bromine can be slightly partially positive, the other one partially negative, going back and forth and so on. However, this is not strong enough of an electrophile. And we'll see later, what we're actually going to be doing is paying an enormous energetic cost to break this aromatic ring, the aromaticity. And so we need to have something that's going to be quite electrophilic as we do that. But we're going to get the energy back in the end. So we're going to pay an energetic cost, but then get that back. So what the iron tribromide actually does is this is going to act as a Lewis acid. So I'll put it down, I'll use green. So remember back from Gen Chem, a Lewis acid is an electron pair acceptor. We've been dealing mostly with Bronsted Lowry acids and bases. It's proton transfer. But this is iron tribromide is going to act as a Lewis acid. So what's going to happen is the bromine is going to donate a pair of electrons to the FeBr3. So we'll end up with something that looks like this here. Now we need to deal with our formal charges. Notice now the iron is accepting a pair of electrons. This bromine is donating. So for our formal charges, this is going to have iron will have a negative formal charge. This bromine will have a positive formal charge. Now, depending on your favorite organic chemistry textbook, you'll see some subtle variations in this step of the reaction. It might be, the electrophile might be shown like this, or sometimes it's shown in a slightly different way to help exemplify what the idea is happening here. Is our strong electrophile is essentially the equivalent of Br+. So you could actually show that here like this. If I remember right, I don't think the Solomon's book shows this step, but I don't remember. So, oops, I'll write that better. But this conceptually helps is that we're actually thinking about this as Br+, which seems kind of unusual. So, and then FeBr4. I'll put this in parentheses. So if you're writing the mechanism, later on, I'll show you, we can either use this structure that I'm circling right now or the one on the right. But what this really helps show, I think, is that this bromine is lacking electrons. It actually has a positive formal charge. So this is going to be a strong electrophile. It really wants electrons. Right, we've seen Br- all the time, and we say, okay, that's a good leaving group. It can accommodate that electron density, but now it's actually missing electron density. So that's going to be a strong electrophile, and that's what we've generated. So now let's try step 2. We have our aromatic compound, benzene in this particular case, and it's going to react with our strong electrophile. So I'm just going to use the first structure here. Rewrite all of this. Negative formal charge, positive formal charge. So now this is the key step. What we're going to have is, I'll write it again down here. Here's our strong electrophile. And benzene is actually going to be our nucleophile. So this is unusual. We've just been spending the last, maybe seems like hours, but maybe an hour, discussing how stable benzene is because of it's aromatic. But what we're going to do now is actually break aromaticity by having the benzene attack and pick up a bromine and then attack that strong electrophile and break that bromine-bromine bond. So let's see what that gives us in terms of an intermediate. And I might have saved enough space here. Actually, I want to draw this a little bit bigger. So one of these two carbons that's involved in this Oh no, I hit erase and then point. Okay, there we go. One of these two carbons is going to be now bonded to the bromine. The other one is actually going to become a carbocation, losing the electrons that were involved in that carbon-carbon bond. So why don't we just put the bromine on the top carbon, the convention. This is all the same, and now we have a carbocation here, plus FeBr4. Now, what's really important here is that we're paying this enormous energetic cost to break aromaticity. This compound here now is no longer conjugated. However, what does help make this a little bit more energetically favorable is, notice we have a carbocation adjacent to a pi bond. So when in doubt in something like this, let's consider resonance. So this carbocation is actually resonance stabilized. I'll use the red arrows here. So we can draw resonance structures. So it's making the best of a bad situation energetically. Not sure what happened there. Okay. So let's draw this resonance structure, the positive formal charge. And we can draw another resonance structure because we have the electrons in this pi bond also adjacent now to the carbocation. Right, so we have this resonance stabilized carbocation, or another name for this is the uranium ion. So if you're talking to your friends over the weekend, probably on the phone or something like that, you can talk about the uranium ion. Or if you really want to impress them with the chemistry jargon, it's also known as a sigma complex. Actually, it sounds more like a problem than a name, but okay. So what ends up happening is that we're paying a huge energetic cost to break aromaticity. However, we're making a bad situation energetically a little bit better by having this resonance stabilized uranium. Okay, so now we're not quite there though, because we've seen the bromine. However, our final product was actually an aromatic compound. So we have one more step. I'll put it here before the page break. We're going to remove the proton, and we'll call it restore aromaticity. Why don't I put a name here for the top one, for number 2? We'll call this formation of the uranium ion. So now I'm going to redraw this same structure here of our uranium ion. I'll just use the first resonance structure. So we have this here. And now what we really would like to do is to restore aromaticity to get that energy back. And a way we can actually do that is, notice this carbon now, as is shown here, still has the hydrogen on it. So we could have something like our iron tribromide that's still around. This will end up forming HBr in the end. It's going to pull the proton off here. We'll use those electrons in the carbon-hydrogen bond to reform the double bond. Let's see what that gives us. So now what we've ended up doing is we reform that double bond, have our bromine, and HBr plus FeBr3. So this Lewis acid is actually acting catalytically. We reform it in the end, formed HBr. And notice now what we've done is we substituted, which was a hydrogen here originally, with a bromine. So this will be a common mechanism that we're going to see for this electrophilic aromatic substitution. We'll form different, I'll make it a little bit smaller so we can see everything here. We're going to form different strong electrophiles, a few different electrophiles. The mechanism of that step will be different, but the goal is the same, to form a strong electrophile. Then in this key middle step, the aromatic compound will attack the strong electrophile. We lose aromaticity, which is energetically unfavorable, but we form this resonance stabilized uranium ion. And then in the last step, we deprotonate to regain aromaticity. And so you can see these carbocation intermediates reminiscent of an SN1 type reaction. So we have 4 minutes left. And then, so for crystals, no, in this particular case, FeBr3 will be neutral. The iron is neutral. It was when it had FeBr4 had the negative formal charge. Oh, you're right. FeBr4, you're correct. That one does have a negative formal charge. So here, once the Lewis acid was attacked here by our Lewis base, then this complex, this Lewis acid base complex, here, the iron has a negative formal charge. Okay, so in the last 3 minutes, that wasn't enough material for today. I thought, let's finish off this week in probably the most exciting way possible with a free energy diagram. I'm looking to see if people are logging off. But no, not yet. Okay. So we'll go through this again, we will in a little bit more depth next time. But if anyone knows, I love free energy diagrams, but I'm so excited I can't write coordinate here. So, but I think this is a great way to summarize what we've been talking about. Kieran loves, okay, excellent. There's one person I know, at least, that likes free energy diagrams. We'll use this here to represent this reaction. So I don't think I can show everything here. This is the downside to one of the downsides to not having the big whiteboard. We're going to form our strong electrophile, but what we're most interested in is step 2 and step 3 here on the profile. That's what we're going to show. And just to highlight that how, as I mentioned a couple